So the talk I'm going to give is from prototyping to deploying, building ML systems, and how Featran can help. So this is a continuation of the talk that Neville gave, basically how to use Featran in practice. All right, so the goal of the talk today is for you all to leave understanding how to use Featran for model training and within a service that evaluates the model. So in order to accomplish this, I'm going to take you step by step through conception to model deployment for an ML-inspired use case at Spotify. So I'm using the word inspired because I'm cutting out some of the details in order to really focus on the feature and Featran related components and let that be the true star of the talk. All right, so a rough outline of what I'm going to be talking about is the following. So first off, defining the problem, which is our use case at Spotify, presenting a ML solution for our use case, talking about feature and model selection, going into the infrastructure that we built, which Neville gave you a bit of a preview for, and then talking about feature and latency in a real-time service. All right, so first off, use case and ML solution. All right, so the goal is to order content on home. And so for Spotify's home, it's structured in the following way. So it has shelves that have like a name such as made for you and you might also like, along with a collection of media items. And so media items are these things, and it's basically any item that you can click on and play. And it's defined by its URI. And so our goal is, given a shelf, order the items to maximize for total shelf consumption time. So basically, we want to put the more popular items at the front of the shelf in order for users to click on it and in the end, listening to more music. All right, so given our goal, an ML solution to this problem could be the following. Step one would be to train a classifier to predict the probability that a media item and shelf pair will be played, and then order the items based off of the probability of it being streamed. All right, so given that this is the route that we're going to be taking, the two ML decisions that we have to then make are the following. First is model selection. How do we even model the probability of a stream given a media item shelf pair? And so the model is denoted by the H there. And then also feature selection, which is given a model, like what are the most informative input features that we should feed into it? And so for the focus of this talk, I'm just going to be on talking about the input features X. So we're going to assume the model, again denoted by H, is just black box, and it's up to us to come up with the right features to feed into it, and then it will tell us what the probability of a stream is. All right, so at the very base level, the types of model features that we're going to need are just the shelf name and the media item URI. We'd also like to add in some additional contextual information, such as the weekday, the time of day, user location, user attributes, and media item type. And so this is going to form the basis of our input feature that we're going to want to feed into our model. Okay, so we're starting with our raw input features, which are, again, like the media item URI, the shelf name, and the side contextual information. And what we want to get is this input feature, model input feature denoted by X. And so that arrow there is where Featran is going to come into play, is how do we take these raw features and then convert them to a form that can be fed into the model. And for the purpose of this talk, you can think of X as a vector of zeros and ones. So that's our end goal, is to go for these raw inputs to a model input feature. All right, so before we started building data services and or data pipelines and services, we first asked ourselves, should we even be doing this? So our current state was, after formulating our ML solution, was to say, we had an idea of what the model and input features should be, but we weren't sure if it would actually work. So the very first step that we took was first we collected just a small subsample of user data from home impressions and from the logs. And so there we had our raw inputs, which was the shelf name and the media item URI and some side contextual information, along with the raw labels, which would be something like how long a user listened to a media item for. And then from there, we initially experimented with model and feature selection in Python using SciPy and sklearn. And that allowed us to initially test out a bunch of different ideas quickly. But again, it then limited us to just a small subset of user data. However, once we were confident in the prototype, then we said, like, let's build it, and that's when feature-end came into the picture. So that leads to the next section of building stuff. So this is the end architecture diagram that we ended up building, but we're going to go through each component of it. So starting off with the common featurization library, in which we have all of our feature information in there, and which uses feature-end. And that's going to feed into two separate components, one the data pipeline and one the shelf reordering service. So then this is here to really highlight that we're using feature-end, I guess, in three different places. One, which is the featurization library, and since that then feeds into the data pipeline and then also shelf reordering service. So let's start with the common featurization library. Okay, so the purpose of the library is to take raw data and convert it to an intermediate form that can then be extracted by feature-end. So hopefully from the Neville's talk, kind of remember that extract is a function related to feature-end, but we're going to go into more detail about it. So to make this more real, let's give ourselves some concrete examples. So let's just say our raw data is going to be information that contains the following. First off, time played, media item URI, shelf name, and timestamp. And then our intermediate representation, denoted by process data, is going to have time played, media item ID, media item set type, shelf name, and weekday. So going from raw data to process data is really meant to highlight the fact that all the data pre-processing and like cleaning is happening within this common featurization library. So an example of that would be, we're going to start with the media item URI and then map it to a media item ID and get its set type. So starting off with something like your daily mix 2, each user has a unique URI. So the first step would be to map it to a common ID that just represents daily mix. And then we'd also get the set type information from it, which is personalized playlists. So those would be then the two features that we work with and not just the URI. Similarly, from the timestamp, we're not going to work with the raw timestamp, but rather extract the weekday from it. And again, this is a simple example just meant to show that there's going to be some data pre-processing, but it should all take place in the same location, which is this common featurization library. And then the very final step of actually getting X, the model input, that's going to happen within either the data pipeline or the service. All right. So we can define two Scala case classes to represent the data. So first off, we're just going to have our raw data represented in the following way. We have our time played, media item URI, shelf name, and timestamp. And then also just have another case class to represent the process data, which has the time played, the media item ID, set type, shelf name, and weekday. So these are two, yeah?
I have a time played and a timestamp. Time played is what duration or just a start time?
Time played would be the duration. But then again, this is kind of like a made-up example, so it could be whatever you needed for your actual application. But let's just say this is how long the user listened to this like media item for. Okay, so then the actual common featurization library, it's going to have our two case classes and then the following two objects. First off is our home feature spec. So Neville talked about how you define a feature spec for, I think you use like a record, but it could also be for a case class. So we're going to find a feature spec for our process data case class. And the types of transformations that are going to happen on it are, first, for the time played, we're going to use the binarizer transformer. So we're going to say, use this to generate the label. So we're going to set it equal to 0 if someone has listened to a song for less than 60 seconds, and then 1 otherwise. And then the other transformations are all just going to be one hot encoder that we're going to use for the media item ID, the set type, shelf name, and weekday. So yeah, first part, just defining your feature spec on this process data case class. And then next off, we have this home featurizer object, which contains the above feature spec, as well as just a utility function that takes your raw data and converts it into the process data. So again, this is just meant to convey that all the pre-processing takes place in the same area, and it's done via this function called process raw data. All right. So the next, moving on to the data pipeline. Right, so the data pipeline, it's going to use this common featureization library. And as Neville mentioned, we at Spotify, for the most part, write our data pipelines using SHIO. And the other input to the data pipeline is just going to say, we have some historical home logs that we're going to take in. OK, so let's see how featurean would work in this case. So the first step is just reading in the historical log data. And then the next step would be getting the raw data and converting it to our process data case class, where again, raw data and process data are defined in our common featureization library. So here we have our raw data, and we're assuming that from our home log inputs, we can get the time played, the media item, URI, shelf name, and timestamp, and just pass it in. And so the next part was just calling this process raw data function. And at the end, we have a S collection of our process data. So a very simple transformation of just going from our raw data and converting it to our process data. And then next off is extracting the data using the home featureizer feature spec. So we're calling home featureizer feature spec to get our feature specification that we've written for our process data. And then we're calling the extract method and passing in our S collection of process data. Right? And then from there, we're just kind of requesting that we'd like our feature values to be returned as, in our application, it's going to be a sparse double. Right? And then from there, the final steps are just saving the training data and also the featurean settings. So you can save your data in any way that you want. A simple way to save it would be to convert it to a string, where the first element is the label and the remaining indices and values are just there for the non-zero elements. Right, so then save the training data and then save the featurean settings. So basically you have a data pipeline in 2 slides, because all of the actual feature extraction, or all the feature engineering component takes place in the common featureization library that uses featurean. So it's very simple to then just write a pipeline that does the mapping for you. OK, so after we run the data pipeline, the 2 outputs for it are like first the featurean settings that we saved, and also the training data. From there, the next steps are using the training data for training your actual model, which I'm not going into the details about. We're just assuming that it's black box, and then saving the trained model. So then the shelf reordering service, the 2 inputs to that are going to be the featurean settings that were used to train the model and the actual trained model itself. And the common featureization library is also going to feed into the shelf reordering service. So on to that then. OK, so one question is, why use featurean in a service itself? What we could do is generate the features for each user beforehand and store that information. That way we don't actually have to construct the features in a service. And there are 2 reasons for doing that. First off, it's computationally expensive to do. So what we do need to store, though, is the raw information about each user and song. And that is OK, because that also allows us to do like feature sharing across different models. So like imagine that you're trying to test out like 10 different models. So if you're going to first save all the features for each different model, it's going to be n times or 10 times the total number of users. However, if each of those models draws from a similar subset of raw features, then they can share that information. It will drastically cut down on the computational cost of storing stuff. But in my mind, the real reason for using featurean in the service that I'm not really demonstrating in this example is for real-time features. So basically, being able to construct features based off of real-time user activity. So asking yourself, what did the user just do, and being able to put that into your current feature. And that you can't save, so you have to construct on the fly. So for these 2 reasons, we went for using featurean within the service itself and constructing features on the fly. OK, so other side notes about services. At Spotify, we write them in Java using Apollo. And we also use more or less like protobuf to send messages to services. So our protobuf in this example is the following. So our first message contains the media item URI and the shelf name. So our daily mix and the made for you, and then an actual request is going to contain a bunch of these repeated home contents. So that's going to be our input to our shelf reordering service, is a bunch of these is a home request. Okay, so let's see how this works within the actual service itself. So similar to the data pipeline, our first step is just to get the data, although now it's not coming from historical logs, it's coming from our request. So first step is to get the home contents from the request. Right, so next is get the raw data and convert it to process data. So again, we have our raw data case class that we defined in our common featurization library. And so one drawback to this setup is there is no label in this point. We don't know how long a user has listened to this song for because they haven't gotten it yet. So we're just going to pass in a dummy label for now. And then same exact thing as we did in the data pipeline, we're going to call the process raw data function. And then in the end, we're going to have a list of process data, which again is defined in our common featurization library. Okay, so the next few steps are, oops, sorry. Where did you go? I do not want to update you right now. Oop, yeah, so get our Java-friendly feature spec. We're going to load our feature settings. So remember again, we got our feature settings from the data pipeline. We saved them, and they were an input to this service. And then again, we're going to extract the data using our Java feature spec and with the feature settings. So in the data pipeline, we just called extract, and now we're calling extract with settings. We're passing in our list of process data as well as the feature settings. And finally, we're also going to request our data be returned to us as sparse doubles or sparse double array. Okay, so as one problem to this current setup right now is in our sparse array, we're going to have to manually strip out the label. As you saw that we inserted a double label in there, dummy label in there. So now we're going to have to, in order to feed it into the actual model itself, we're going to have to remove that and do some indexing by one. So that is not good and motivates for why we use the multi-spec feature. So we're going to keep it the way it is for now, go back and correct it towards the end of this presentation. But you don't want to do that. The service shouldn't have to know about the label. So the multi-spec is going to help us get rid of that. Okay, so then after we call featurean, what happens next? I'm not really talking about this because then this moves beyond the scope of the feature generation, but we go from a sparse double to a form that can be passed into a model. We get the model scores, return the home content with the scores, and then reorder our content using the scores. Okay, so now let's look at them side by side to just see how similar the functionality of using featurean is within the Shio data pipeline, which is written in Scala, and the Apollo service, which is in Java, because they do have a very similar functionality. So the first step was just, again, getting our data. In the data pipeline, it came from historical home logs, and in the Apollo service, it's coming from the request. But then the second step is the same. We're putting that data into our raw data case class defined in our common featurization library, and then we're calling the process raw data function. And in the end, we're either going to have an S collection of process data or a list of the process data. Okay, so in the service, we have to get our Java-friendly version of the feature spec, which we don't have to do in the data pipeline. But then also load the feature settings that we got from the data pipeline. And then the next two steps are pretty similar. We're again calling the extract method, but in the Apollo service, we're calling extract with settings. So we're passing in both our process data and the feature settings. And then also we're, in the end, requesting that the extracted feature values be returned to us in the form of a sparse vector. And the extra step that we then have to take in the data pipeline is to save the feature settings as a text file. since that is one of the inputs to our Apollo service. All right, so hopefully it shows you that feature is easy to use in both a pipeline and a service. But we're not done with this story. As we saw in the service, we had to do a manual extraction of that dummy label. So let's see how we can then go back and correct that. But first, let's get an overview of what we just went through, so they'll have a better idea of when we go back to see what we're looking at. So we started with our common featurization library, which is where we defined our Featran feature spec and also contained all of the data preprocessing utilities. We used our common featurization library within our data pipeline that took historical home logs and converted it into a form that can be read by a model. So the output of our data pipeline was the Featran settings that I used along with the training data. From there, we used the training data to train a model. The output of that would be the trained model itself, and both the Featran settings and the trained model go into the shelf reordering service that is written in Java using Apollo. So this is just the overall architecture and the flow of it, but we're going to get to kind of see it again by going back and correcting our mistake. So that brings us to multi-spec. All right, so first off, why are we using this multi-spec Featran feature? Case one is what we ran into. I will note that the progression of these slides are based off of real life events. So if you're saying, why did you write these slides like this? It's, well, first off, we didn't know about the multi-spec feature in the first place. And I guess it kind of helps seeing how you would go back and just easily correct something. So really reinforcing the way that this flow works for all of you. But yeah, so the first case for using it is that you want to be able to separate the training specific information from the model input feature. And so training specific, that would be what we had the labels, and you could also have something like a weight that you'd want to use, which is only specific to the training. And then you have your input specific, which are, you know, the actual inputs to the feature, or input features to the model. So in our example, that was just the one hot encoding of all the other features that we saw, right? And the second case would be if you're training an ensemble of models. So if your end model, in this case, the diagram is a linear combination of two separate models. So where each separate model takes in a separate input, denoted by x1 or x2. And so you'd want to keep these x1 and x2 features separately, and multi-spec would allow you to do that. Okay, so let's see how we can not strip out the label in the service, and that's starting with the common featurization library. So I showed you that we defined two case classes to represent the data. We had our raw data and our process data. So the first step to fixing this is just to break up the raw data into two separate case classes. One, the raw input, and then secondly, the raw label. So the raw label contains only the training specific information. And the raw input has our media item URI, shelf name, and timestamp, which is going to be used to generate the actual input feature to the model. And then with our process data case class, we're just going to say it's time played now is an option of a double, and you'll kind of see why later to make our life easier. So the major change we had to do there is just going from one case class to two case classes. Okay. And this was our feature spec from the old common featurization library. It just contained all of the information together. So now, as you can guess, maybe the trick is just going to be, you know, make two feature specs. So the first one is label specific, and the second one is input specific. So note, though, that both of these feature specs are defined for the process data case class. It's just taking different components of it and putting it into a feature spec. So in our label, we're going to request an optional of time played, again using our binarizer transformer and saying the label is going to be 0 if the threshold is less than 60 seconds and 1 otherwise. And our input feature spec is the one hot encoding of our media item ID, set type, shelf name, and weekday. So again, very simple, just break it up again. All right, yeah, label, input. Okay, so let's, also make a change to, yes. our home featurizer object. Got confused there. So now the difference between the old one and the new one is this feature spec. It contains two separate feature specs. Before it was just one that had just for the label and input feature, but now this feature spec has input and label separated. And our process raw data, the main difference here is now it's taking two inputs. It's no longer raw data, but separately our raw input and then our raw label, which is an option, and the default is set to none. So still similar. Again, it's just breaking things up. All right. So now that we have our changes in our common featurization library, let's move on to see multi-spec in the data pipeline. And so you'll notice there wasn't anything that said multi-spec in the common featurization library. It's just kind of preparing the changes that we would need to make for the data pipeline, which uses the multi-spec functionality. So let's see what we'd have to change in our data pipeline to accommodate for this. So this was the old way where we read in data. The new way, very similar, except now we're taking our input to our process raw data is not going to be raw data. It's going to be raw input and then an option of raw label. So a very minor change. Okay. And then going side by side, looking at the differences between the old way and the new way. And this is where the actual name multi-spec is going to come into play. So still need to get our feature specifications. In the old way, FS was just one feature spec. In this new method, FS now contains our input and label. Again, we want to call the extracted component. So in the old way, since FS just contains one feature spec, we don't have to do anything special and just leave it where it is. In this new way, we're defining a multi-feature spec and just passing it in the label and the input. So this is where it comes from. And similar in both methods, you call extract, giving it your S collection of process data. And in the end, you either have a feature extractor or a multi-feature extractor. So still very similar, just a few subtle differences. And the major differences are what you're going to see when you then call on the extracted, requesting your feature values in the form of a sparse vector. So in the old way, because you just have a single feature spec, you're just going to get, a single sparse vector. Where now in the new way with the multi-feature spec, you're going to have a sequence of sparse vectors, where the first element in the sequence is going to correspond to the label, and the second element is going to correspond to the input. Right? So then you just have to, the example, we mapped our sparse vector input to a string representation. Again, just the inputs are a little bit different from this, either just one sparse vector or a sequence of sparse vectors, where the size of that sequence depends on how many feature specs you passed into your multi-feature spec. And you save your settings in the same exact way. And so those are the major changes in the data pipeline you'd have to make. Okay, so now let's see what happens in the shelf reordering service. So this was the old way of reading in data where our home contents came from the actual request to the service. Here we had this dummy label, which shouldn't be in the service because the service shouldn't have to know what a label is, since it's only there to actually evaluate the model. So now this is what we've not quite been leading it to, but you can just pass in the raw input. And so it doesn't have to know anything about the label. And then also how we get our Java-friendly version of the feature spec, right? So we just, in the old way, called home featurizer feature spec. And now in the new way, you call it the feature spec again, but just request the feature spec for the input. And so if you do this, all the other steps are the same, but the big win here is that you no longer have to manually strip out the label and shift the indices by one. So this is why you should use the multi-spec feature, right? So now let's look at how fast is featran in a service. So the application I'm working on is for reordering content on home. So that has to, every time you come to your home page, return results within, I'd say like 1 or 2 seconds. But there are a bunch of other services that are called to generate the home page. So this should take very little time if we can actually use it in practice to re-rank. So we've been testing, playing around with this in testing. So the results I'm going to show you is for an A/B test that we ran. So it was on 3% of all incoming home traffic. We had just over 26,000 features. And each request required getting scores for either like 150 to 200 home content messages. And so I'm going to show you latency results for service steps that involve the feature engineering components. So the first feature engineering component would be converting the home content to our process raw data. The second step was when we called the feature extract method on the process raw data, and we got our list of sparse floats. And then for our application, we're using TensorFlow. So the next step would be from taking the feature sparse float output and putting it into a TensorFlow tensor. Okay. So the code, I will note that the code written in this presentation is meant to optimize for readability, which is not necessarily the case in the actual service itself. So there are a few changes that we made in order to speed things up that are not shown in this, but I will kind of point out some of the areas. And the first is we have to use a Java list when converting to process data. Okay, so on average, it took under 10 milliseconds, and this again was for around 150 to 200 items per request. So pretty fast for the first component of just, using, this is just in the common featurization library of going from our home contents to our process data case class. Okay, and then the next was calling the feature extract method. And we'll say that we used a JRecord extractor, which was initialized when the service was launched, so we don't have to use the extract with settings each time a new request comes in. We just load it once and then have it there within the service, and that we called the JRecord extractor on each individual process data. So it didn't take a list, we would just iterate through it and ask it for a feature extraction one element at a time. And so this on average was under 15 milliseconds, so pretty fast. And finally, the tensor building, which I didn't show you any code for because it's somewhat specific to your application of what you want to do next, that took under 5 milliseconds. So overall, the feature building latency is under 30 milliseconds. So we found that this is fast enough to use for a real-time service that serves homepage. Okay, so at the end now, so hopefully now you understand how to use feature for model training and within a service that evaluates the model. So what we started with was just stating the problem, which is wanting to re-rank content on home. We then provided an ML solution for that given problem. Before we started building anything, we validated the hypothesis on a small subset of data, where we actually worked in Python using sklearn and scipy for our feature engineering. And then once we were confident, we developed the system architecture, which really had the three main feature components, which was the common featurization library that fed into both of the data pipeline and the service. And then showed that feature is fast enough to use within a real-time service. All right, thank you. Questions?
Coming back to your latency benchmark at the end, for this total of 30 milliseconds, is it for all the feature and for the 100 and something contents?
Yes.
So you extract the feature once and then you compute that for all home pages? And how do you schedule that to reach that number?
So the way that it worked is, I'm still not sure how, it's basically so we have multiple backend systems on different machines. Every time a request would come in, that required generating scores for 150 to 200 of those home contents. And then from there we would return it. So this is we had multiple, I guess we can go back. You'll see that there are actually multiple lines because it's per machine and then it's per average request time.
If we just use the training model and there's a box over there, you can see detail. You can tell what you know about the training model, what you are using behind it.
Yeah, so we're using TensorFlow. Our model is a factorization machine because we kind of want to start out simple, and factorization machines let you generalize from just like kind of like a basic linear model to adding in more contextual information with larger features. And so from there, like so after you train the model, if you're familiar with TensorFlow Lingle, you have to like freeze it, and you get like the protobuf version. We then give it to the service. So when at any time like a request is, like the next steps are we're using like a sparse implementation of it. So you got to get like your 3 TensorFlow tensors that represent the indices, the actual values, and the shape of it. You then like load that onto your graph, run it, and then get the scores.
Have you ever tried different models?
No, this is still new. So I guess like what we have tried is we experiment with different orders of factorization machines, but no, just factorization machines.
Okay, thanks.
No problem. All right then. Thank you.